I've been working in this field for about 30 years. I have read all the papers on islands, talked to almost all the people I could talk to, and I still can't put together a coherent story. And if you talk to an average string theorist, they actually did not know the derivation of Hawking radiation back from Hawking's original paper. Very few theorists had actually worked through that calculation. I think this reason came from the fact that people drew a wrong lesson from ADS CFT duality. And the wrong lesson is the following.
So, welcome to Phymaths podcast. Today, our guest is Dr. Samir Mathur. He is a theoretical physicist at Ohio State University, and he is well known for his fuzzball paradigm. And he also works on black holes, and he is also well known for his small corrections theorem in the late 2000s. And he also works on numerous areas like cosmology. So, first of all, Dr. Mathur, it's great to have you on the podcast.
Thank you. Happy to be here.
So before we talk about anything else, can you tell me about your active projects right now? So what are you working on nowadays?
So right now, I am in the middle of a paper which I'm finding very interesting to write. As you might know, the whole question with black holes always has been, what can possibly happen at the horizon? And I think we finally found an answer to that. So in terms of fuzzballs, we have now a conjecture as to why, when you follow the semi-classical rules of collapse, something actually goes wrong at the horizon. Not at the singularity, where of course you would expect something to go wrong, but something actually goes wrong at the horizon. And whatever leads to this new effect at the horizon is also going to create new effects in cosmology. So for half my time, I'm working on understanding things like the cosmological constant. And for the other half, I'm trying to understand this final step in the resolution of the information paradox.
So correct me if I'm wrong, but in the fuzzball paradigm, there is no horizon. So what do you actually mean by, what's happening at the horizon?
Good. Yeah, so that's exactly the question. In the normal picture of the black hole that people used to have, all the mass was at a central singularity and there was a horizon. So now you can first ask the question, if I just construct the eigenstates of the theory, the time-independent solutions having a certain mass in string theory, do they have a horizon? And the old no-hair theorem used to suggest that you will have a horizon, but in fact, with fuzzballs, you find you don't get a horizon. So you get a nice, like a stringy star, but there is no horizon. So on the one hand, you could say this solves the problem, but not quite. There is still one last step which is left, which is, what about the dynamical evolution? So suppose a shell is collapsing under its own gravity. It doesn't see anything special. It would appear at the horizon and it keeps going in all the way to the singularity. So the question is, what stops this dynamical collapse? So even if we have found all the energy eigenstates of the problem and found them to not have a horizon, you have to still explain what goes wrong with the semi-classical approximation, which seems to show that a shell would just smoothly fall through its horizon. So I think we have now isolated the effects which will cause a shell to do something funny at the horizon. So of course we have to use the fuzzballs in our thinking, but the question is, how does a collapsing shell transition to a fuzzball? Here you have the shell, there you have other solutions which are the fuzzballs. Now there must be some mechanism which tells the shell, as you're collapsing, don't keep collapsing through the horizon, but turn into a fuzzball. Like, who tells it to do that? So that was the crucial last step in the information puzzle. And I think we have finally gotten a handle on that.
So are you working on the dynamics of the tunneling of these things to different fuzzballs?
Yes, it is very much connected to tunneling in a way. So the first thing we had noticed some years ago was that, well, there is something very interesting about black holes. The entropy of a black hole is very large. It's this large number given to us by Bekenstein. And so the number of fuzzball solutions, because they represent the microstates of the black hole, they are correspondingly large. And so if you try to estimate what is the probability that a collapsing shell will tunnel into one of the fuzzballs, you can actually find the natural suppression you get from the large action of these massive objects is exactly sort of cancelled by the large degeneracy of states you can tunnel to. So as a first estimate, you find, it is possible that something new happens and a collapsing shell can tunnel into fuzzballs. But that's not the whole story. Because now you have to ask, will it actually do that? And what is the mechanism of that tunneling? So for example, if I give you a potential barrier in quantum mechanics, if you take a particle which is quite far away from the barrier, it won't tunnel across the barrier and reach on the other side at that time. Only when it hits the barrier and feels an obstruction, then it tunnels in. So you have to actually see there's to first be a barrier and then you go. But if there is no barrier, then as you are going in and in and in, as the shell is collapsing in, you would ask, why can't it just continue on its path? If there's a barrier, you can then ask, how do I get through the barrier? What do I tunnel to? How long does it take? And there the estimates show that you can do very interesting things because of the large entropy of black holes. But first you have to ask, where is the barrier? And that is the question I think we now got a handle on.
I see. So you also mentioned in the start that you are also working on the problems regarding cosmological constant. So there is this recent study that got a lot of attention about DESI from DESI, and they said that the cosmological constant may be dynamical. So what are your thoughts about that?
So I was actually very excited to hear that, because we have written a couple of papers on trying to understand the cosmological constant using whatever fuzzball theory is telling us. But it has always been very hard for us in those models to get a cosmological constant which is constant. It never is constant. It keeps changing. And so we were always perplexed. How do we manage to make this get a value which is sort of always going to try to get fixed to the value W equals -1? If it is not a constant, it certainly opens up the field to being able to use fuzzball theory to explain the cosmological constant. But I would say that is also true for many other attempts to explain the cosmological constant, because it's very hard to sort of imagine that W has to be exactly -1 if you don't just start with a lambda in the theory. So I was actually quite excited because we were always having difficulty in getting exactly constant cosmological constant. And if indeed these results hold up and it's not a constant, then it would work much better for whatever we were trying to do.
I see. Okay, so now I want to start talking about one of the main problems that you have been working on for a long time, which is which is related to black holes. So you had this paper in late 2000s, I think in 2009, where you proved this small corrections theorem. So you can talk about that, but in simple words, I can describe for my audience that small corrections theorem effectively says that you cannot get away with information paradox just by introducing some small corrections. But one thing that I want to ask, I mean, you can also talk about what the theorem is, but one thing that I want to ask is that Hawking's paper came in the mid-70s, I mean, which is almost 50 years from today. Why do you think that this theorem took so long to be proven? I mean, was it only because people were not paying a lot of attention to this theorem, or is it because somebody did not bother to do something like that? So why did it took so long to prove a theorem like this?
I think that's an excellent question. And I think what happened was the fact that there were essentially two communities trying to work on roughly similar problems, but from completely different sides. So if you look at the general relativity community, this GR community, they had sort of believed that, okay, we can't find a way around it. The entanglement of Hawking pairs is going to keep rising. We do have this information loss problem, and we are going to live with that. So they had sort of, a lot of GR people, perhaps not all, but a lot of them had accepted the fact that information is either lost or trapped inside the black hole forever. And there were models for that. They would say there could be baby universes inside where it gets trapped and so on. But they were not trying to really make it come out in the Hawking radiation because they saw no reason that it would actually come out. So they were not really trying to find a hole in Hawking's calculation. On the other hand, people who worked in string theory, They came from the side of particle physics, where things just scatter, everything is unitary, and it's all just scattering of objects to objects. And they thought that whatever happens, the information has to come out in the Hawking radiation. But then they never went back and looked carefully at the kind of derivation that Hawking had done to get his information puzzle. So in some sense, the two communities were not really talking to each other. The general relativity people didn't really understand how the string theorists had managed to prove, for example, the entropy of extremal black holes, the work of Strominger and Waffa. And if you talk to an average string theorist, they actually did not know the derivation of Hawking radiation back from Hawking's original paper. Very few theorists had actually worked through that calculation. So the string theorists were not used to quantum fields on curved space, which is what Hawking's derivation comes from. And the GR people, of course, had never understood how D Branes can give rise to entropy. And so I found this very interesting situation that the people who actually work in string theory had never really understood why the general relativity community was so strongly worried about this problem. And so to explain to the string community that you can't just hide the problem away. So what the string community really believed was, oh, there must be some small subleading corrections and they'll take care of the problem and it'll go away. And so to prove to them that, no, in this case, the GR people were thinking correctly, that at least if you put no other new physics at the horizon, it won't go away. I derived the small corrections theorem. But the difficulty with the small correction theorem, the reason why it wasn't proved before, is that it does require a bit of heavy machinery. And the machinery you have to use is a strong subadditivity of quantum entanglement entropy. Now, in the theory of quantum information, most theorems are actually quite easy to prove. They are either obvious or they take 2 lines to prove. But this is the one thing, the strong subadditivity of quantum entanglement entropy, which does not have an elementary proof. So in fact, it requires a 10-page lemma, and then based on that, you prove a 3-page theorem. So because it is not intuitively obvious, and because one has to use this machinery, I think it was never very clear to the string theorists that they could not really escape by using small corrections. And so even to this day, many people have not absorbed the importance of that theorem. They still keep trying to use the semi-classical black hole as some kind of an approximation or some kind of emergent approximation, and then hoping in some way that would still be compatible with getting a unitary evaporation of the black hole. So I think a lot of papers today are actually making mistakes in what they're doing because they're not really absorbed that this actually cannot happen.
And when you mentioned that string theorists were actually thinking that small corrections can take care of this problem, that includes, some big short string theories. I think you said somewhere in some podcast that you had this email exchange with Ed Witten because he was also thinking along these kind of lines that small corrections can take care of this problem, right?
Yes, indeed. I was actually giving some lectures at CERN in 2009, and then just after that, Witten wrote to me. I mean, he's always very courteous and very polite. So writes me this very polite email, which is essentially trying to say, why are people worrying about this problem? And then I tried to explain to him over several emails that, you have these pairs and you have this entanglement. But in spite of the fact I was sending him these long emails and PDF little files, I really could not communicate the fact that, small corrections cannot fix it. It actually required a proper proof. And so that's when I sat down with the textbooks of quantum information and tried to work out a proof. And it turned out not to be immediately obvious. But it didn't take that long. In about a month or two, using all the things which were there, one can, using this strong subadditivity, actually make a proof. So what I would like to see is that more people should absorb the lessons of that theorem, because even to this date, there are many people in the string community who are somehow thinking that, subleading saddle points or something. We keep hearing these words, but after all, a subleading saddle point is just some Euclidean way of finally saying that there is some effect in the actual theory, which is always Lorentzian. You can always use a Euclidean argument. You can always see a saddle point, but in the end, you are trying to say that it has some effect in your Lorentzian evolution. And if it is a subleading saddle point, it has some exponentially suppressed evolution. So all those words are simply saying that some small correction is going to take care of the problem. And I think people need to understand that no, you cannot do that. If you try to force through some small corrections and fix the problem, it may appear to you to be possible through some kind of saddle point, but the moment you try to see what you're really doing, you'll find you're doing something very wrong. You are either trying to say there's big non-locality, things can disappear inside the black hole and magically appear at infinity. So if you look at some models, it turns out that's what they are secretly doing without actually knowing that they are doing that. Or you're actually losing unitarity, or you're using an incorrect dot product. There are all these things which are going on. But there is no actual way to get around the fact that no small correction to the Hawking pairs is actually going to get you unitary evaporation.
I'm sure you're talking about the islands paradigm. We will talk about that. But there is one thing that I want to come back to. So you said in the start of my last question that, a lot of people from the GR community have not learned string theory very well. So do you think that probably it's we have made it hard for them to learn string theory? Or is it not the case?
No, I think so. I think that it is quite easy to at least convey the essence of, for example, the Strominger-Waffa calculation of how one computes the entropy of an extremal hole to somebody in the GR community. I have tried to write review articles which are actually aimed at the GR community. If they sat down and they actually worked through such a review, I mean, it would take a couple of weeks. They would know the derivation of the Strominger-Waffa calculation down to the last factor of 2. But I think people feel that if they have to learn string theory, there is a steep learning curve, because you have to either learn all about D Branes strings, quantizing strings, ghosts, and so on, or accept some of those things at face value. So it turns out if you just learn the metrics produced by branes, but don't bother to learn in detail all the other aspects of string quantization, you can learn enough to understand how the Strominger-Waffa entropy was derived. And that's the approach I actually took in the review articles I wrote. But I think somehow the communities have become a little far from each other, in the sense that apart from a few people, there are some very good GR people who do know string theory very well. They're just very few of them. But other than that, I think the two communities are still moving on different paths. They are asking their own questions, the GR community, and those questions are not directly of interest to the string people, and vice versa. I think that gap can be closed. I think it should be closed. It might help to hold a summer school or something where people from both communities come and learn the basics maybe of black holes where both communities intersect. It would be good if that could happen.
Okay, so now I want to come to your, one of the famous proposals that you have, the Fuzzball proposal, and that proposal is consistent with your small corrections theorem. That you're not just introducing some small corrections, you are literally introducing this new structure inside the black holes. So one question that I want, I will request you to describe for the audience what fuzzballs are. But I have one question about it. So I think the first paper about the fuzzballs came in the late 90s, probably in 1997. That's way earlier than your small corrections theorem. So what I want to ask is that, did you actually know the small correction theorem in 1997, or were the motivations to propose this idea were different from small corrections theorem?
So I had been working on the information puzzle for quite some years before 1997. And I had tried to solve the puzzle through all the techniques known in GR and in string theory. But because I had worked through Hawking's computation in detail, as far as that computation went, I was on the same wavelength as the GR community. I did not believe that if you have small corrections, it can actually get the information out. So that was a confusion which only those string theorists had who had not actually studied the problem in great depth through Hawking's argument and then trying to fix it and so on, because they were doing other things. String theory is so wide, they could be working on some other aspect of string theory. But anybody who had actually spent a long time trying to work on the information puzzle through the original Hawking's calculation and trying to find an error in it, I think they already knew that small corrections will not fix the problem. So what happened was, when we finally found that when you take the actual states in string theory, the Strominger and Waffa states, We actually start with states which were even simpler. The states found by Ashok Sen for the two-charge black hole, an even simpler black hole. When we started finding that those guys were fuzzballs, to me, that was a solution to the puzzle, because I knew that you can't fix it with a small correction to the horizon. And now when we are actually trying to find what the states of the black hole look like, the same states which were counted by Strominger and Waffa, when you try to see what they actually look like in string theory, you find they are completely different from the normal classical picture of the black hole. In fact, there's a complete change at the horizon. There isn't even a horizon. So to me, it was an instant solution, and I knew it had to be the correct answer. But what happened was all the string theory people who were not familiar with the problem itself, they found this to be too radical, that there should be a big change at the horizon. So then they said, look, this is too radical. Maybe the states you have found so far, which you are showing us as explicit constructions of fuzzballs, are just special things which happen to have, funny things at the horizon, but the other states will have good smooth horizons. And so that was the belief, that most states would still have smooth horizons. We were just looking at very non-generic constructions, and that's why we were finding them to be fuzzballs. But if we looked at very generic states, they would start still again behaving as if they had a horizon. And so then to dispel that, the small correction theorem came up. Because the impression had been that if you look at very generic states, they somehow might have small structure at the Planck scale, but overall, when you look at it over long length scales, the length scales involved in Hawking's calculation are on the scale of the entire radius of the horizon. So for a solar mass black hole, you're talking of low energy physics on the scale of meters to kilometers. At that scale, everyone thought, or actually the string theorists thought, that whatever microstructure might be inside the fuzzball, it would actually behave like essentially smooth space-time at long distances. And the small correction theorem tells you, no, that can't be. If it actually, whatever microstructure you have, if it behaves like smooth space-time at long distances, you cannot solve the puzzle. Because if you have smooth space-time at long distances, you will get Hawking's effect at long distances with small corrections. They were then trying to hide the entanglement problem in those small corrections. But a small correction theorem says, no, even though you're emitting a lot of particles and you're making a small correction to each of them, just because you have a lot of places to hide the entanglement doesn't mean you can get away with this. The entanglement will have the same problem that Hawking initially proposed. So Hawking's argument is actually rigorous. You can make it like a rigorous theorem. If you don't have an order unity correction at the horizon, then you cannot solve the puzzle. So to me, the small correction theorem sort of was a complement to fuzzballs. With fuzzballs, you can only make some constructions explicitly. In 1997, we had just found that by rough arguments, in string theory, we found effects which show you that all string states would try to swell up to the size of the entire horizon. That was not the same as having an explicit construction. Then later, when we started doing the constructions of the states one by one, we constructed all states of the simplest black hole, the one found by Ashok Sen, and then some states for the larger black hole found by Strominger and Waffa. But it's very hard to find all the states for all the possible black holes. It's a near impossible problem. And so people kept saying, no, the other states might still have horizons. You haven't found enough states. That's a very hard question to answer. But that question is what is answered by the small correction theorem, because the small correction theorem tells you, if you find even one state which does have a horizon, you are going to lose unitarity. Because you take that particular state, that one will lose unitarity. So your overall theory is not unitary. So it somehow tells you, here are examples of how you can break the no-hair theorems in string theory and how you get the fuzzballs. And the small correction theorem tells you, well, all the other guys better be like this, otherwise there is no way out. So together, the two actually made for a full solution to the puzzle.
I see. So one question that I will have immediately is that these people who think that, if you find more states, they will have horizons. An immediate question that arises is that how does this transition happen from a state that has no horizon to a state that has a horizon? So do you think that this question is a fruitful question to ask?
So good. So that is a little bit of what I had started when we started talking about when we started our discussion. You can ask a dynamical question, like if a shell is collapsing, how will it transition to fuzzballs? Right? So if you ask that question, then yes, that's a very interesting question to ask. That's what I've been working on the last couple of years. We try to answer it through something called the vector hypothesis, which I can talk in more detail about a little later on, if you like. But if you're not asking a dynamical question, then let's see, what do we mean by transition? The other way you can talk about transition is by a change of coupling. As you know, in string theory, the coupling constant is a variable quantity. So first, just consider extremal black holes. So here you take a bunch of strings and branes at weak coupling. Everybody would agree that it's just some bunch of objects sitting in the middle of this room, like any other bunch of atoms. And then you start imagining in your mind that you'll slowly increase the coupling and follow the wave function of the state as you change the coupling. Suppose some computer could make you these wave functions. What do you expect? So when I started at weak coupling, I just had flat space-time and some strings and branes sitting on it. When I increase the coupling a little bit, the gravity is now stronger. Maybe it will be sitting inside a little dip. So there'll be a little gravitational dip. As I make the coupling stronger, the dip will get even deeper. But just by continuity, because everything is supersymmetric, you can imagine there'll never be a place where suddenly the dip will change to having an infinite depth. But the traditional black hole, the semi-classical black hole, even the extremal one, has a throat of infinite depth. And not only is the throat infinite, after that there is a horizon. And after the horizon inside, there's a region inside the horizon. And then inside that is a singularity. And now you can see how strange that sounds, because when you just go through this slow process of changing the coupling constant, step by step, the throat gets deeper and deeper. But unless there's some kind of sudden phase transition somewhere, it can't change to suddenly becoming infinite, developing a horizon, developing inside the horizon, developing a singularity. How would all that happen? So the moment you think about it this way, you can see that string theory is telling you that at least extremal black holes must have at the end of a deep throat what we call a cap. Okay? And so when we started finding the microstates for the extremal black holes, which is what we started first, because the Strominger-Waffe black hole and the Ashok-Sen black hole were all extremal black holes, well, that's what we found. People had been writing the metric for these black holes, which were just the normal black hole metric with infinite throat and a horizon at the end. But what we started finding was the throat was not infinite, it was just deep, and at the end was a cap. And the shape of the cap was different for different microstates, and that's where the information about the state was. So in a way, going back to your question, how does something become something? There are two ways of becoming. You can either just imagine that you are changing a parameter like the coupling, and then this is the path. It doesn't change. It becomes a fuzzball because at weak coupling, you have a bunch of strings and branes. As you increase the coupling, what we found to our surprise was instead of shrinking and becoming smaller, the brane cluster actually expands. With the coupling, it expands. And roughly, you can understand by saying that the tension of many objects in string theory goes like 1 over the coupling. So as you make the coupling weaker, objects become lighter, have a lower tension. They can stretch more, go further away. And so as you change the coupling, what we found was the bound states were actually swelling up. And they were swelling up in such a way, this was a 1997 paper, the size of the bound state, it increased with the coupling. It also increased with the number of branes you put in the object. That may not look so strange. But the interesting thing was, there were 7 parameters that we were using at that time, different kinds of branes, different compactification scales, the coupling and so on. But the size of the bound state was just the same function of these 7 parameters as the radius of the corresponding classical black hole. So that's when we learned that that's where we surmised the fact that string theory is trying to tell us the size of string bound states is always of the same order as the size of the horizon that you would expect on classical grounds. So perhaps there never is a horizon. So that was the paper of 97. And then later when we came back and started constructing these states one by one in the work with Oleg Lunin in 2000 and 2001, then we started seeing, indeed, you just get these deep throat with caps, and the caps hold the information of which state you have, and you never actually develop a horizon.
I see. I mean, one thing that you mentioned in your answer was that you said that unless there is a phase transition, but somebody may say, yeah, okay, there is a phase transition, then what?
And you could say that, absolutely. So that's why I started with BPS things. In BPS things, people don't normally expect a phase transition because there's too much supersymmetry. If it is not supersymmetric, somebody could say there is a phase transition, absolutely. And many people did say so. And that's why you have to first construct some non-extremal states as well. And here the work of JMARC, there was a group of people, Jejala, Madden, Ross, and Titchener, called JMARC for short. They constructed non-extremal states, and they also were fuzzballs. They did not have a horizon. We don't know too many non-extremal states, but we know quite a few right now. They don't have horizons. But this is where the small correction theorem comes in, because we can't construct all the states of all the black holes, particularly the neutral ones. But then on the other hand, if any black hole actually did have a horizon, the small correction theorem tells you that you cannot save the unitarity of string theory. So it just tells you what to aim for, that if you are arguing that you will have a phase transition and develop the horizon back, then you should be aware that at that same time you're arguing that you will not be able to solve the unitarity of string theory.
I see. Okay. Okay, so in the mid-90s, there was this work by Susskind and some other people on this idea called black hole complementarity, which essentially says that there are two realities, one for the person who is far from the black hole and one for the person who is falling into the black hole. And then a lot of people actually work to, prove that this idea is actually not right. For example, the firewall people did some work in the early 2010s. Okay, so in your work on fuzzballs, there is something called fuzzball complementarity. And you have this conjecture that it may happen for some reason that a person falling through the fuzzball may feel as if that person is falling through empty space-time. So, but don't you think that this will have the same problems as black hole complementarity, or do you think that this is different?
So it is interesting that it is different. So the difference is the following. What Susskind was trying to do was say that there are two realities. In one description, you actually can go into the black hole. And in some other description, you stay only outside the black hole. So there are two descriptions of the same system in which you go into the black hole and the whole space-time exists. The outside, the inside, the horizon is all there. And there's some other description which only the outside exists. And these are somehow two complementary descriptions. The observer who's falling inside, he can just see the inside, but some other way of encoding those degrees of freedom only shows you only the outside. Now, he didn't have any proof of this. And right at the time he was proposing this, a lot of people said, look, this can't work. I told him this at the same conference where he proposed this. A lot of other people I could see were also telling him this. And the reason was basically the same as the one which was then again brought up in the firewall argument in a very precise way later in 2012. And the reason was, well, go back and ask about Hawking's pair creation. If you do look at Hawking's pair creation, that's the information puzzle. One member of the pair falls in, one member falls out. So look at the description in which you do see the infalling guy. So that one, you do see the horizon. Go to that description. In that description, if you're going to create entangled pairs, then the entanglement of the radiation with the inside is going up. That's what Hawking told you. Now you can have any other description you want where you don't have the inside and so on. Let's not even think about that. There is one description where you have a horizon. In that description, you will get the entangled pairs. And what are you saying about it? So I raised the same question in some review articles too. But somehow what happened was that the groups who was working in Stanford, all the people who were working with Lenny at that time, they were very much focused on what happens to somebody falling in. But they never actually focused very much on Hawking's original question, what is happening to the radiation which is coming out? That's where the paradox really is, right? So what is happening to the entangled pairs? And what the firewall people did was they produced a very clean argument, making this very rigorous, that if you look at the entangled pairs, then you actually cannot have, the entanglement will keep rising. So they just pointed out Hawking's original argument back to Susskind, saying, look, if you have a smooth horizon, and if you have complementarity, in one of the two pictures, you have the horizon. In that picture, you will get entangled pairs. Then they use the same bit models, which I was using for the small correction theorem. And then they use that to show, look, the entanglement will keep rising. So it was just the same as the Hawking argument given back to Susskind. And then he realized that, oh, if we have a smooth horizon, we will have a problem with Hawking pairs. The issue was that we knew about this, several years ago, because we of course knew there were fuzzballs and we knew the complementarity arguments as well. But we had a different version of how some part of what Susskind was doing could be saved. And that argument we had tried to make in the following way. Hawking radiation happens with low energy quanta. At infinity, they have the same wavelength as the radius of the black hole. So for a solar mass black hole, they are 3 kilometer long wavelength quanta. So they have an energy of the order of kT, where T is the temperature of the black hole. K is the Boltzmann constant. So what the small correction theorem tells you is that if you go down to the wavelengths of interest in the information puzzle of order KT, okay, then those quanta, they simply cannot see a smooth horizon. Because if they did see a smooth horizon, if you had good physics at low energies, you will be back in Hawking's puzzle, because then you will get the creation of pairs, and the small changes to that can't save you. So we already knew that. But what about particles of energy much bigger than KT? So now we split the problem into two. Particles of energy of the order of KT will not see a smooth horizon because there isn't one. So it's not that there are two realities or anything like that. It's just that there is just one reality. You can write the entire metric. We wrote the metric inside the fuzzball, outside, in between, everywhere. We wrote the complete metrics. It is not the vacuum horizon. So it's simply not the old metric. It's not complementarity. We're not saying in some picture you can see the old metric. So the metric is different. And now the point is that the quanta of energy KT which are emitted, they're not emitted from the vacuum. They're not emitted by the method of pair production in the vacuum. They actually are emitted from the surface of the fuzzball, just like particles are emitted from a piece of coal. And so there's no information puzzle. So for particles of energy of order of KT, it's completely different from Susskind, and it solves the puzzle. But now let's ask if it is possible at all that if you have a particle of energy 1 million KT, and it comes and hits the fuzzball, what happens now? Now, what the firewall argument was trying to argue was, they said this guy will actually burn up and he cannot actually see any smooth inform. So what did that mean? They were taking Susskind's argument still at face value, that inside the black hole, there are lots of complicated degrees of freedom. The question is, can you rearrange them in some such way that when this guy comes and falls on it, the effect of some combination of those degrees of freedom, the way they are evolving, they could mimic the fact that the guy continues inside. So it's not like those degrees of freedom are actually showing you a vacuum there, but could this evolution of the infalling observer be mapped to an evolution which looks like infalling evolution to some leading order? So fuzzball complementarity already told you at order KT you can't do this. The firewall people are trying to do it both for order KT and higher. Okay. For order KT, you can't do it still by the small correction theorem. So let's forget that. You can't do it. And they also agree. That's fine. But what the firewall people also said was, if energy is much bigger than KT, well, even then you will burn up. But there was a flaw in their argument. So they had, and the flaw was the following. We wrote a paper about it, myself and David Turton, a couple of years later in 2014. It's actually titled The Flaw in the Firewall Argument. They used the fact that after a black hole has been there for at least half its existence, all the degrees of freedom inside the black hole, assuming it was like a normal object, are entangled with something outside, the early radiation which has already left. And in that case, they proved by a very clever argument that in this situation, you can't rearrange these degrees of freedom to behave as if this looks like an effective vacuum. Because these degrees of freedom are somehow already spoken for in terms of how they entangle with something far away. So you can't really rearrange them into some combination which will make it behave like an effective vacuum. That's just one, a rough way of like laying out the elegant arguments they were making. But there was a mistake. And the mistake is the following. If you're coming in with an energy which is very big, let's say 1000 KT, then you actually bring in new degrees of freedom with you. Because if the old black hole had a mass m, it had an entropy which was given by the surface area for m of order m square. The entropy is order m square. So the number of states is order e to the m square. If you bring in a particle of some mass delta m, now your total entropy is the entropy correspond to a mass m plus delta m. And the number of states is now exponential of this new entropy. And you find by a very short calculation that suppose you brought in something of energy 10 KT, 10 times the Hawking temperature, the new phase space available to you with this new energy added as compared to the old phase space you had before you added this energy, the new phase space is 10 times larger than the old phase space. So
that will change the radius, right?
It changes the radius. So the horizon forms at a radius outside, but if you just count the number of bits that you have, because the firewall argument was in terms of bits, you find that 9/10 of all the states are not entangled with anybody. If they were entangled with somebody, their argument was correct. But if you bring in something of energy 10 KT, you'll find that 9/10 of the space is not entangled with anybody. And so then, now it is still possible. It doesn't prove that it will happen, but it's at least possible that you could rearrange these 9/10 of the degrees of freedom to give you an evolution which up to 9/10 accuracy looks like free info. And 10 kT is still a very low energy. You send in something of energy 1000 kT or something heavy, because kT is such a low temperature. You have a lot of phase space to make these. So the entanglement argument they used wasn't correct. And so we also made a bit model. I have a paper called, I think it has something about bit model in the a model with no firewall. I think the paper is called. It gives you a bit model as to how you could actually take a system and throw in something of energy much bigger than kT on it, and it actually looks as if it is giving you smooth infall in the interior. Now, we don't know if this model is actually what is happening with fuzzballs. That's too complicated for us. But just to show you where the flaw in the firewall argument is, new degrees of freedom come when you bring in something of energy bigger than kT. And the fact that they can possibly, in principle, they can rearrange to give yourselves smooth infall, you can make a bit model to do that.
Right. I mean, correct me if I'm wrong, but they were including the new effects of quantum gravity at the old radius, but they should have done it at the new radius.
Right? Absolutely. So what they did was they were trying to maintain causality by saying that if a particle is falling onto the surface of, let's say, some object, which is like a fuzzball, it hits the surface. Before it hits the surface, no quantum gravity effect should happen. They thought that looks quite logical, because they said all quantum gravity is confined to the region of the fuzzball, and outside is effective field theory. So until you hit it, nothing should happen. It sounds very reasonable, except that flies in the face of the information puzzle. Instead of a particle falling in, it's easier for me to talk of a thin shell falling. So suppose it's under thin shell of mass delta m falling onto a fuzzball of mass m. If the new quantum gravity effect started only when the shell hit the surface of the old guy with mass m, the old guy had a radius which was almost 2m plus a Planck length. But once you add this mass delta m, which let's say is 0.1 m, after it hits the surface, well, where is the new short shell radius? New short shell radius is at 2.2 m. So whatever new physics it does after hitting that surface, it just can't send that information out anyway. So they had assumed unitarity in their firewall model. They said, we want to save unitarity. That was one of their first axioms. If you don't want to save unitarity, of course, you're back to the GR people that, you have nothing coming out in the Hawking radiation. They want to save unitarity. But the moment you say that no new effect will happen till you hit the surface, you've already given up on saving unitarity and causality. So because the region of the effective field theory outside, the light cones are normal. They said, I have effective field theory outside the surface of the fuzzball, which means the light cones are the normal light cones, which means if some shell of mass 0.1 m comes in, it will create a horizon at 2.2 m. You simply cannot escape anymore. So it was an internal trap. So we know that whatever new effects quantum gravity has to create when a shell is collapsing, it should do it at the new horizon. If you wait for it to do it at the old horizon, it will never help you. And this was always a problem with the information puzzle right from the beginning. If a shell is collapsing, it goes smoothly through its horizon radius. Suppose you assume that because nothing seems to be happening at the horizon radius, you can always imagine something new happens at the singularity, because that's the singular place. But whatever new thing happens there, it can't solve your puzzle anymore, because the horizon, you can't reach it anymore. It's outside the light cone from you. The light cones inside the horizon point inwards. So no signals from the singularity can now get out to the horizon and change the physics over there. So that was one of the essential issues of the information puzzle all the time, that the collapsing star or collapsing shell passes smoothly through the horizon, but after that you are trapped, because the light cones turn inwards inside the horizon. And so whatever you do later on at the singularity or anywhere inside, it will never send its effect out back to the horizon. If you never get rid of the horizon, Hawking pairs will keep getting created and you can't get out of the problem. So in a sense, the flaw in the firewall argument came for the same reason. If you try to assume you have effective field theory, which means normal semi-classical gravity, outside the surface of this object, whatever it is, the new infalling observer will create a horizon which is outside this and be trapped, and you can never get your information out anyway. The moment you allow the quantum gravity to happen at the new horizon, you have all the new degrees of freedom which are between the old and the new horizon. They are roughly given by the entropy of the new horizon minus the entropy of the old horizon. As we said, that's a big number. and the exponential of that is the amount of phase space. And those guys are not entangled with anybody. So no entanglement argument can actually prove to you that complementarity for observers of high energy will not happen.
I see. Okay, so there's this paper by Suvrat Raju in 2021, and he actually mentions in that paper that there is this property called the split property. That is a property of some quantum field theories, and he says that that property actually has been assumed in Hawking's argument, and that property has also been assumed in believing that the page curve should happen, right? But he says that that property is not true for gravitational theory. So what are your thoughts on that?
So actually, I must say I'm not familiar with the term split. So, but I have read some of Raju's papers. I cannot claim to understand everything. But in the end, I was not in agreement with most of the things that he says, because he seems to be arguing that even with just ordinary semi-classical gravity, there is a kind of non-locality that is not expected from normal quantum field theories. And so he was arguing in some recent papers that by sitting at infinity and making observations and just doing experiments at infinity, you can flip a spin sitting at the origin without light having had time to go all the way to the origin. So he was saying that gravity has this kind of a non-locality that if I want to flip a bit which is sitting at r equal to 0, if I can make arbitrarily complicated experiments at a large radius, capital R, I can actually acausally flip this spin. Now, I might have misunderstood this, but I thought that he did say this. And it was sort of based on the fact that he was allowing himself to make measurements at infinity arbitrarily quickly. And so his arguments were based on the fact that if I have two different spin states, they couple differently to the quantum fields around them. And these quantum fields, of course, stretch all the way to infinity. If I make a sudden projection onto some particular quantum state at infinity by doing a measurement, I can project onto any part of the quantum wave function that I want. And in particular, I can project onto the part which is spin up versus spin down in the interior. So he was saying that for reasons like this, gravity has an inherent non-locality that we are not otherwise familiar with in quantum field theory. And I think if this is the argument, and I should say if, because I don't want to, since he is not here talking to us at this moment, I could be misunderstanding. But if this is the argument, the place where I would worry is that you can't always do measurements instantaneously and measure what you want. So for example, if you try to measure something at a given time and say, I want to measure the state of this object, in a relativistic quantum field theory, what ends up happening is you end up disturbing the vacuum, and half the time you end up just picking up vacuum fluctuations. So if you say that given zero time, an infinitesimal amount of time, I can actually exactly measure, let's say, the energy of a given state or some other property of a given state, it's not true. In quantum field theory, if you try to make a detector to measure something very quickly, the energy of that detector in trying to make that measurement will actually pull out particles from the vacuum and disturb the state rather than actually tell you what the state was doing. So I think in some of these assumptions, some assumptions might be underlying this, which may be the source of the difficulty.
Well, so what I understood by what he means by a split property is that he says that suppose that you have a Cauchy slice, and then you take a bounded subregion of that Cauchy slice, and then you will have that bounded subregion and its complement in the Cauchy slice. The split property says that you can specify the state on that bounded subregion and its complement independently. That's the split property.
Okay, so I think then that's very much in the line of what I was just talking about, because then he used exactly this to kind of think to argue that if I want to change the state in a given region in the interior, and I have access to things which are outside, by doing complicated experiments on the outside, I can change the state on the inside without actually having time to send a signal in and bring them out. So that was the application of, I think, what you're calling the split property. But I think the place where that claim runs into trouble, I think, is the fact that the kind of measurement he says, I can do this, I can make this projection, or I can do this measurement. I think exactly those kinds of measurements we have known in quantum field theory you cannot do.
I see. Okay, so we talked about the small corrections theorem, but there is another term that comes comes in the discourse of black holes, and that's effective small corrections theorem. So, what is the difference between small corrections and effective small corrections?
Okay, so what happened was that in the beginning, people were not comfortable with fuzzballs because they thought that this is too radical a change at the horizon. And so then the small correction theorem came and told you you do need a radical change at the horizon. But then some people started wondering, and slowly people came to the idea that everything, all the states really are fuzzballs. And over the years, I did see this change in the viewpoint of people. They said, okay, everything is a fuzzball. Let's agree with that. But then the viewpoint became, okay, they are all fuzzballs, but that may not be a useful description of them. As we said in the context of some other discussion we had a few minutes ago, it might be that at the macroscopic scale, they are all different and they have all these structures that we found when we were making fuzzballs. And so they don't have the vacuum horizon. But perhaps for low energy experiments done around the horizon, they effectively behave as if they were smooth space-time. They were like the vacuum. So the picture would be that suppose you had, let's say, this table out here. At the macroscopic structure scale, it would have atoms in either this place or that place, and different fuzzballs could have atoms in different places. But if I tap the table and I make it just oscillate in some kind of smooth, long wavelength sound waves, they might be the same for everybody, and that might just reproduce the semi-classical metric that you write down for the standard classical black hole. So if that were true, then you would go back to saying that at low energies, you would get the same quantum fields in curved space that Hawking used. And then you can ask what happened to the entangled pairs. And so you will get the entangled pairs. And then you can ask, then how are you getting out of the entanglement problem? And you would again be forced to go back and say there are some small corrections hiding somewhere. So there can't really be a way out around this. But still, many people have started saying the exact description of string theory states are like fuzzballs. They are just like pieces of coal. They don't actually have a horizon. But at low energies, they effectively behave as if they have a horizon. But even that is not possible. And that's what we call the effective small corrections theorem. There is no effective dynamics possible of these complicated fuzzballs, which at the energies of order kT, the energies that are relevant for Hawking evaporation, will give you an approximation of smooth space-time around the horizon. That's not possible.
I see. Okay, so now I want to start asking you about some of the alternative approaches that people are working on. So I'm sure you know about of course you know about the approaches that people use which are motivated by ADS-CFT to solve the black hole information paradox. And I think you have said in the past that these approaches don't work. Some of the reasons that you have given are that in ADS-CFT you have a correspondence between a gravitational theory and a non-gravitational theory, but in this particular problem you have to have a correspondence between a gravitational theory and another gravitational theory, right? And in the ADS-CFT, you also have this correspondence between vacuum and vacuum, but that's not the case when you are using, ADS-CFT for black holes. So are these the only criticisms that you have, or are these the major criticism, or do you have some other major criticisms on using ADS-CFT to solve these black hole problems?
Yeah, I think these things you mentioned are just some aspects of things you can ask about, but they are not really what I would call the central difficulty I have with that entire approach. The approach was that I simply couldn't reproduce the calculation. So I tried to read those papers very hard and just try to understand what do they mean. So let's just start with the fact that you have the black hole, you have string theory. I think they would all accept you have string theory. And then you're evolving and you write the semi-classical picture. And the semi-classical picture, you say the outside is normal flat space and inside there is an island. Now, if you look back and see what is an island, the island is nothing but the inside of the black hole that Hawking used in his picture. It's just the inside of the black hole, some part of it. So sometimes you may not take all of it, but whatever part they take, it doesn't really matter what part you take. For all purposes, even though island looks like a new word, it's just the inside of the black hole. What they do with it, will be important for them to call it an island. But the region, as far as that is concerned, when you actually use an island, it's just the region inside the black hole. Okay, so let's see what is the claim. So you're having this normal Hawking pairs, they are evaporating. One member of the pair will go inside, so it will fall in the island. And one member of the pair goes outside, so the entanglement is growing up. Okay, and now you ask, okay, so what are you saying? I have to say something. And I don't get an answer. So I talked to all the people and read all the papers. And I still don't get an answer. What are we saying? And so what happened was people started saying different things. So it turned out that not everybody is saying the same thing, and that may be the source of the confusion. So some people are using Euclidean arguments and trying to argue that in Euclidean arguments, you find a new saddle point. And this new saddle point somehow tells you that the entanglement entropy will come down. So you try to write down a calculation of something which will give you the entanglement entropy. You compute that using a Euclidean path integral. And that Euclidean path integral has a new saddle. And you use that to say the page curve comes down. Okay. I try to do this and I cannot reproduce the calculation. Because what happens is, at the starting point, you want to recast the entanglement entropy in terms of a Euclidean path integral. But I find that whatever the path integral they are writing is not actually giving the entanglement entropy that you wanted. More precisely, people are trying to compute Rényi entropies and take the limit of that to get entanglement entropies. And that's completely fine. So let's talk about the simplest Rényi entropy, S2, the second Rényi entropy. There's a certain path integral which will give you that Rényi entropy. There's a certain other path integral which they write down, which gives you a different quantity. And it's not the same path integral. So you're not computing the same quantity. So then I tried to go and ask, like, what is going on? Why are we computing this different quantity? And then they said, they meaning, there are many different people. So not everybody is saying the same thing. So let me not pin this on any one person. These are more like my confusions of what I couldn't understand after trying to get a grip on what's going on. Okay. So it looked to me that it's the wrong quantity. And then I was told that the postulate is that this quantity, which I'm calling the wrong quantity, which is not the second Rényi entropy, the postulate is that this quantity in gravitational theories does become the Rényi entropy you want. But that is completely circular. You're computing a different quantity, an incorrect quantity, which is not the Rényi entropy you want. And then you're saying our postulate is that this is what computes the correct entropy in a gravitational theory. So then you go and ask, why are they saying that? Where is that postulate coming from? And then if you track back as to where it came from, why they want that to be the way they want to get the entropy, you find they're assuming a certain dot product in the gravity theory, which is not the correct dot product. So if you have
an amplitude.
Pardon? Yes.
It's an amplitude, actually, right?
It's an amplitude. So what is happening is if you have two different systems, one here, A and B, and then you have two other systems, A prime and B prime, and they have nothing to do with each other. There's a dot product which is A dot with A prime and B dot with B prime. They're two completely different systems. Mm-hmm. There's no reason to also have a term where A dots with B prime and B prime dots with A. But they have added that term in. So if you go back and ask where did this term come from, what does this new amplitude correspond to, and you go back and see where it is coming from, you find the quantity you are actually getting is not the Rényi entropy. Instead of trying to compute trace rho square, which you wanted, you have added to it a piece, trace of rho whole squared. And when the matrix is big, which is what happens after the halfway evaporation point, the trace of rho whole squared dominates over trace rho squared. And so the part which you added extra by hand, which was not supposed to be there, becomes the dominant answer. And then it looks like the page curve has come down. So let's push it further, because I don't want to immediately say that's wrong. We have to go back to the reasons as to why one is trying to say this. So then you ask, what is this new term there and what is it doing? And I got two kinds of answers, which I tried to trace down to their ends. One was that if you try to compute the normal coarse graining of the entanglement entropy in the lab, these are papers of Hong Liu and so on, some very nice papers, which tried to argue they're using old results in the StatMech community. If you have two systems A and B, and they're entangled in some state, but then you try to coarse grain over those possible density matrices. And when you coarse grain over them, you find that when you try to extract the coarse grain entanglement entropy, let's say that for the secondary entropy R2, there are two terms added together. And the purpose of those two terms which you get after this averaging is that when A is bigger than B as a system, the entanglement entropy is given by the degeneracy of A. But when B is bigger than A, when B is smaller, then the entanglement entropy is the degeneracy of B. So we of course know that if you have entangled two systems with each other, the entanglement can at most be the entropy of the smaller system. So you have two terms, and it just tells you that the smaller one entangles maximally with the other one. It's just an old statement of the Page theorem. So you try to see what are the different pieces coming into this calculation, and there are certain contraction of indices doing something in this particular story, which is a well-known story, and you find this contraction of indices is not the one which is being used in the gravitational path integral. So things look similar, that there are two terms here, there are two terms there, but from what I could figure out, these terms are not those terms. So then I went back to look at the papers of Marolf and Maxfield and Marolf. There's some very nice papers they wrote because those papers were Lorentzian. And really, you should really ask the question Lorentzian to really understand what is going on, because the Hawking problem is a Lorentzian problem. You cannot even set up the problem if you don't have Lorentzian evolution, because there's no horizon in the Euclidean black hole. It comes from the Lorentzian section. And then when I read those papers, it seemed that he was doing something actually very different. So for him, it seemed that if you have two objects far away in the universe, something is here and something is at the other end of the universe, they're actually talking about the wormholes which actually physically go from here to there. This was an old story done in the around the late 80s. People worried about wormholes that could connect distant parts of cosmology. And they gave rise to ensemble average theories. There was old work of Coleman and others from that time. So Marolf was visualizing this as actually the exact gravitational path integral having contributions where a wormhole goes from here to a distant far away place. Okay, so this actually tells you that the actual exact gravitational theory will be an ensemble average theory. If you remove the effect of these wormholes, you can write as a local theory, but then it is ensemble averaged, or you can not ensemble average, and then you have these non-local connections as wormholes. When I took this over to the...
But these wormholes will, violate the assumption that you need lab physics at infinity, right?
They will. They do all kinds of things. And in fact, the fact it's an ensemble average theory, it creates troubles of its own. Right? Mm-hmm. So you could say that violates what we normally would like from the lab. But then the people, I took this to the people who were doing the island theory, and I asked them, is this what you mean? Normally in string theory, I don't have ensemble averaging. I just take type 2B string theory with certain definite compactification, and I start from there. There's no ensemble averaging. Are you really saying there are wormholes in the type 2B string theory path integral which will take me from one place to the other faraway place, arbitrarily faraway place, if I just put the full string theory in the computer? Is that your picture of string theory? And they said no. And so I just did confirm at least this, that Marolf's wormholes are different from the wormholes that are coming in the island picture. Marolf's wormholes are actual real wormholes, and the wormholes coming in the island picture are some kind of effective wormholes coming out of an averaging. But the wormholes that they are getting out of averaging are not the same combination of indices which I get from the StatMech people when they do averaging of two systems, and they get two possible things which they get added together, and they change which system is bigger and how the entropy changes. And then I find that I take this over to the second Renyi entropy path integral, and I find it's not the correct Renyi entropy. So I went through the entire circle of lots of different papers. And if you ask me what's my objection, it's not an objection. I just couldn't extract a story from it. What I would love to do is to just be able to sit down and talk to all the folks in one room and just go on the blackboard from the beginning and see, okay, just tell me from the beginning, what are the assumptions? What's the conclusion? Let's work it all out on one sheet of paper and just write it down in one place. And I can't find it anywhere. If the page curve really comes down by such a simple argument, we should be able to start from scratch and just write down the proof in one place, so that everybody, myself, but also all the GR people, we should all agree that it comes down the page curve by such an argument. But I think that's not possible. And I think the reason it's not possible is that I actually found a counterexample. So if you take 1 plus 1 dimensional gravity, the same one which was used for the CGHS model in the past, there, if you remember, this is the work from the early 90s. So I'm not sure if you'll be familiar with that. But 1 plus 1 gravity plus scalar fields can be solved exactly. And it was solved by the CGHS and later the RST models. And you find the page curve goes up, just like was expected from Hawking. But this time the quantum gravity was solved exactly. So now you can ask, if the page curve in this exact theory of quantum gravity, which is 2D gravity, now these people are also talking about 2D gravity all the time. So I asked them, if I take your 2D gravity and I put it in the computer and solve it exactly, your JT gravity or whatever you're using, will the page curve go up or come down? And I don't get a unique answer. Half the people say that if you take my JT gravity with scalar fields and you put it in the computer, the page curve will keep going up. And half the people say the page curve will come down. In my opinion, the page curve will keep going up. Because those who said the page curve will come down, they said that's on the grounds that the old CGHS models and so on, they didn't take into account topology change. But we pointed this out in one of our papers. Topology change does not change any of the conclusions. In 1 plus 1 dimensions, topology change just means you have a line segment, you can break it into 2 pieces, and you can join the pieces back. There's nothing else they can do with topology in 1 plus 1 dimensions. You go back and you follow how the Hawking pairs were being created and how the entanglement was growing, it keeps growing. So here's a simple counterexample. Here's a gravity theory. You can solve it exactly. It is 2D gravity, and the page curve keeps going up, even though you've included topology change. Come back and tell me now how a 2D gravity argument has told you that the page curve comes down. So the other people who say, no, if you put this in the computer, the 2D gravity, JT gravity, the page curve will go up. Then you say, really? The page curve will go up for the 2D gravity, but you're using this to actually prove the page curve in the full theory will come down. And they say, yes, because what is happening is in the full theory, it comes down, but the rules of the full theory can be somehow extracted in some effective way in the 2D theory, where in the 2D theory, we don't follow the normal rules of gravity, but we change them. So what they say is that we are not going to honestly compute the Renyi entropy in the 2D gravity theory. We will use this, what I was calling the wrong path integral for Renyi entropy. But our postulate would be that this wrong calculation in the 2D theory gives the answer for the correct calculation in the full string theory. And so that's why we have proved that the page curve comes down. This is where I finally understood the conjecture was, but how do you prove that this wrong calculation in 2D is going to give you the correct answer for the 10D theory? It completely beats me. So anyway, these are my confusions. And all that we need is for all these people to get together and produce one clean document which tells us from the beginning to the end at a textbook level, something that every senior undergrad can read. Let's start from the beginning and see what is the argument that the page curve comes down. At every step, we'll write down everything with the assumptions. I can't seem to make it.
So there are some other objections that you have talked about, regarding the island program. And in one objection, you said that at every step they change what they have on the island. They, instead of having, an entangled bit, they have a bit either in the 0 or 1 state. So is that also true? And if that's something that that, don't you think that they should know about it as well?
Yes. So I have had this discussion with many people about what exactly is happening with the island. And as I said, everybody gives a different answer. So again, whatever I'm saying should not be blamed to any one person. It's just that different things are not consistent. So as I said, the island is just the inside of the black hole in the case where the island exists. I mean, so they're doing a flip. At some point, there'll be no island. At some point, there will be an island. But when the island is there, it's just the inside of the black hole. So after the black hole evaporates past the halfway point, there is an island. So let's assume that's the one we are interested in. But then people have been writing the state of lots of bits on the island inside. And they're saying, okay, this is the state inside. And at infinity, they have some bits from the radiation and they write the state for that. But the simplest question I had for them was back to Hawking's original question. Okay, now let's wait for one more time step of evolution, one more entangled pair is created at the horizon because they do want a smooth horizon. So they agree they will have one more entangled pair at the next step. One member of this goes out to radiation. Other member will go and fall on the island. So the state on the island at the next time is not something which is arbitrary up to me. It is coming from the state on the island at the previous time. And I'm just repeating what Hawking did. This is exactly Hawking's construction. In some of the calculations that I saw done, the state on the island at an arbitrary time was just chosen arbitrarily. Now that doesn't make sense because after all, we are saying there's a smooth horizon. That it means no more and no less than the fact that as you evolve, pairs will be created. A smooth horizon is the same as pair creation because that's just quantum fields on curved space. And so what comes on the island at step t+1 will have a new bit, which is entangled by an entanglement log 2 with the bit which has been radiated. This is the old Hawking puzzle. So let's just keep asking in terms of islands, what is going on? How is the page curve coming down when we can actually see that at every next step, another new entangled pair is being deposited with one member on the island and one member at infinity. But then the answer I typically get is, well, the island is no longer the interior of the black hole. The black hole doesn't actually have an interior. The island is just representing something to do with the radiation outside. So don't look at these bits. They don't actually mean anything. But in that case, I want to know what it does mean. Because if you say that the inside doesn't exist, then you have said the whole black hole is like a piece of coal. But then what are you trying to solve? If from the beginning you said the information paradox is not there because the black hole is like a piece of coal, well then, why was there a puzzle in the first place? The puzzle came because the low energy evolution showed you that all the mass falls to the center and leaves you a smooth horizon. If you're saying, no, you have a piece of coal instead, then you have to come and do what the fuzzball people were doing. First, show how you can have something with no hair which doesn't collapse, which is the constructions we did. And then you have to perhaps come and do what we are doing now, show what goes wrong with the collapse process so that you actually make fuzzballs instead of making that black hole. Then you can say it's a piece of coal. Okay, but if you've shown it's a piece of coal by doing what the fuzzball people did, then after that, what is there for you to do? It's a piece of coal, there's no problem to solve. So somehow they seem to be saying, we'll assume it's a piece of coal. They call that the central dogma. If you assume it's a piece of coal, you already assume that somebody else has solved the information problem for you. Then you ask, okay, so what are you trying to do with it? And what they seem to be trying to do with it to somehow argue that this can again be made compatible in some way with a smooth horizon. So either you can try to say that some effective degrees of freedom of this will mimic a smooth horizon, but the effective small correction theorem tells you that's actually not possible. So then you go back and look at what exactly are they doing? How are they actually mimicking it to a smooth horizon? And then there was this paper which I found very confusing called the AEHPV paper, Akers, Pennington, Harlow, the combination of various authors, in which they tried to make a bit model to show what they actually mean by saying that you can somehow map the problem of a piece of coal down to something which has a smooth horizon. So I found the paper at least very clean in the sense that it just bit models. So I can at least read the paper. So it's very good they tried to make it very explicit. But it didn't, my confusions only deepened at the end of that because the model looked to me very strange. It only involves bits. It starts with something which is a piece of coal and therefore radiates unitarily. And then they want to say they can map this somehow into Hawking situation where you actually get entangled pairs. And the claim is that if you can make this map, you can somehow understand how having a piece of coal, which you expect to get in string theory, is compatible with Hawking's calculation. But if you go and look at the details of this work, there's no property of the black hole used anywhere. The same map that they used here, I can use it equally well for a cup of coffee. I can map a cup of coffee into the Hawking evaporation because anything whose page curve goes up and comes down, they're just assuming the black hole like a piece of coal. They're taking any property of the fuzzball. It's just like anything which has a curve which goes up and down. You can go and map it to something which is going monotonically up. And the map is very simple. If you have lots more degrees in one system, you assume the black hole has a lot more degrees of freedom. You can map all the degrees of freedom here injectively into a larger system. You can always map a smaller Hilbert space into a larger Hilbert space. But what does all this have to do with a black hole? If you look at the bitmap, you can make the same bitmap for a cup of coffee, for a car, for a truck. You can map anything to anything, but you can map anything to Hawking's black hole. But the same map, you can map actually any smaller system to a bigger system. You can map a car to a truck. And so I don't understand. So I think people really need to sit down and talk about all this together to say what happened. Because if I talk to anybody in this community, because they're saying different things, I'm not able to extract a story. So I would love to be able to extract something. Anything non-trivial would be great for me to get, because any progress in black holes I'm always very excited about. But I have not been able to find anything. And I think it's largely because everybody's saying different things.
So if somebody asks you that, can you explain in simple words that how does the page curve go down in fuzzball paradigm? So what would you say?
So there it is completely simple, because there it's just behaving like any other piece of code. So we have papers from about 2008 or 2010 where we actually compute the Hawking radiation from some very simple fuzzballs, in fact, from the JMART solutions. And you find that you are not actually getting the radiation from a situation where you create a pair and one member falls to the singularity and one member goes out. In fact, there is no horizon. It's just coming out from some other process. In that case, it was ergo regen emission. The rate of radiation exactly matched the Hawking rate expected for that microstate down to the last factor of 2 and pi, but the process is completely different. So just like what happens for a piece of coal, when you emit some particle from a piece of coal, the state of that particle depends on what was happening at the surface of the coal. The whole point with Hawking was you extracted the particles from the vacuum, and so they had no information of what was inside the black hole, because what was inside the black hole was sitting at the central singularity. That's not what you have now. So with fuzzballs, there is no problem, because whenever you see something leaving, which we explicitly see with the fuzzballs, for which we compute the radiation, it depends on the state of the fuzzball that you had. We took a different fuzzball, we got a different radiation. Because actually coming out of the degrees of freedom on the surface of the fuzzball.
I see. Okay, so there's one thing that we were talking about a while ago, and I think that I should have asked this question at that time. But you said that the proof of strong subadditivity is not intuitive. I mean, it's a long proof. And you said that that's probably the reason why people have not internalized, the lessons from that theorem. But then I was thinking about something like the spin statistics theorem. Spin statistics theorem is also not easy theorem to prove. Its proof is a bit long, but people have internalized that one. So why do you think there is this discrepancy between these two theorems? Is one more abstract than the other? That's why.
That's a good question. I'm not quite sure. I think it is the fact that somehow people have tried to push a story on black holes, which is going in the wrong direction. So maybe I'll try to say why they went in the wrong direction. But I think if they actually stop to look at the theorem, they would understand it as easily as they would understand spin statistics. In fact, there's a very nice intuitive physicist proof of this strong subadditivity by Kalyan Rama. This is from about 8 or 9 years ago. And it's a physicist proof because it's not a real proof. If you have three systems which are entangled with each other, but not with a fourth system. So the strong subadditivity is non-trivial only when there are four systems entangled with each other. But if you have three systems entangled with each other, but not with a fourth system, you can actually write a bit model for how the entanglement is going and explain how the strong subadditivity inequality comes out. So you can actually give a mental picture of how it works. So if you really want to understand the theorem in some intuitive way, it's possible. And though, of course, the proof is not simple. That's why it was proved only in the late 60s or early 70s. It's not an early theorem. On the other hand, I think the reason why people are heading in the wrong direction and always trying to see that they can get a smooth horizon, I think this reason came from the fact that people drew a wrong lesson from ADS-CFT duality. And the wrong lesson is the following. In the beginning, ADS-CFT duality, of course, gave us something very interesting. In one picture, you have D branes. And if you have a large number of D branes, the dynamics is quite complicated. You have open strings between them, and you have millions and millions of open strings acting on millions and millions of D branes. It's a complicated system. But you can replace the D branes by just smooth anti-de Sitter space. And so if a string comes and hits a lot of D branes and breaks up into a large number of open strings, It's a huge mess to compute in Yang-Mills theory. But in the dual gravity theory, you simply have the same graviton going smoothly and falling into smooth anti-de Sitter space. Looks like such a simple description. So I think this suggested to people that the black hole might be similar. Again, going back to ideas of complementarity, there'll be some very complicated description like the fuzzball or whatever you want in the gravity theory. But then instead of doing all those complicated things, there might be a simple effective description where you just float freely through a horizon and you just go inside. So people are simply not able to let go of that idea that just like in ADS CFT, there's a complicated description and there's a simple description. People still would like to think that even if you can have very complicated fuzzballs or unitary theory in some way that you have, why can't there be another description where you have a smooth horizon? And it's very important to understand that one has to let go of this very tantalizing belief. The small correction theorem tells you you have to let go of it, but we can also see the reason why it is wrong. And the reason it is wrong is the following. The way it worked for ADS CFT, suppose you start with lots of D3 branes and you throw something on it. The D3 brane started off in a unique state, which was the vacuum state. And then when you throw something on it, even though it appears to create a lot of open strings, so it looks very messy, it's actually not messy. It's some very particular combination, those open strings all bound to each other by strong interaction into one particular shaped blob, not an arbitrary mess of open strings. And that blob evolves and spreads on the surface of D3 branes in a very particular way. Now that's what happens in the dual map. You send in a graviton, it goes down into the ADS, and goes deeper and deeper as the blob is spreading on the D branes, this complicated open string blob. On the dual theory, you're just going deeper and deeper into ADS. But you had only one state of the D3 branes, so a unique evolution on that side, and you had only one state, the ADS on this side, so you just had infall into that unique geometry. On the other hand, if you take a black hole has an entropy. So surface of the black hole, if you go inside that, there are e to the s different possible states. And the whole information puzzle comes because you don't want to lose that information. When you throw things onto it, they're going to behave in e to the s different ways. You can't map them all into the same way. So if you replace that object by a smooth vacuum in any effective language, you lose the difference between all of those states. And then, of course, you lose the information. So the point is, in a system with no entropy, like the case of just cold D3 branes, you can map them to a dual ADS and you can smoothly go in and you can enjoy the ADS safety duality. For a system with entropy, you should never make that map. There is no way to simplify it, because if you simplify it, you've lost that information. So the no analog of ADS safety duality should tell you that there's a smooth interior to the horizon. In fact, for the fuzzballs we make, we can see this very explicitly, because for two-charge systems, we know all the fuzzball states. In the beginning, when you start down the throat of the two-charge geometry, you are falling down, and in the geometry, and in the dual CFT, you have some very high-frequency excitations which are spreading on the D3 branes. At some point, the excitations on the D1, D5 branes. At some point, the extension of the D1, D5 branes reach the energy scale at which you already have some excitations on the branes, giving you the entropy of the state. At that time, there's no unique evolution there. It depends on the state that you have. If you look back to see what's happened on the gravity side, that's the time you reach the depth of the cap, and the cap is different for every microstate. That's actually the location of the horizon for the two-charge system. So for the two-charge system, you can see this very explicitly. When you reach the horizon scale, all the microstates start differing. You cannot replace them by any one geometry. At higher scales, when you're up higher up in the throat, you could. They were all the same geometry. Once you go inside the horizon, you can't replace them by one geometry, and nor can you do it on the CFT side. Depending on the state you have, you'll interact with the particles differently depending on the state. So this idea of ADS CFT that you want to somehow get a nice smooth geometry emerging as an effective theory, my belief is that this might be at the back of some intuition that is making people trying to get effective descriptions of low-energy descriptions of this. But as the effective small correction theorem proves, there is no way to get a description of the quanta of energy KT involved in the Hawking process and the page curve and all the things we're talking about. There's no way to get any description of those in the low-energy effective theory with semi-classical physics at the horizon. It's simply not possible.
So what will be your reaction if tomorrow somebody, has this black hole construction in string theory that has a horizon?
I would be very interested. I would love to see how it works, because the moment he shows me a horizon, I will see pair creation and I will see growing entanglement. And I already know from small corrections, which is just ordinary mathematics, that the entanglement cannot go down just because of small corrections. The black hole have to keep evaporating because energy is coming out. So the black hole getting smaller. Once, most of the energy is gone, like 3/4 is gone, you don't have enough degrees of freedom to get the information out. I don't even know what can happen. Then you need something bizarre, like, some kind of non-local wormhole takes everything trapped inside in the baby universe and dumps it out to infinity or something like that. Or maybe leaves it in a baby universe inside. So things like baby universes are being believed in by GR people. They leave the information inside the black hole. But I don't think they are compatible with string theory, because if you believe in ADS CFT, then for a given amount of energy in the boundary, you only have a given number of states, because the Yang-Mills theory has only a given number of states at a given energy. So in the dual bulk, you only have a given number of states, which means you can't really have a baby universe with infinite amount of degeneracy for a given mass. So these things which our GR people play with are not really allowed in string theory. So if somebody gave me a black hole construction like that, I would be absolutely amazed. I would love to know what goes wrong then.
So I have this question, but that's more less about physics, but more about the sociology of theoretical physics nowadays. Do you think that a lot of people are just writing papers that may have major errors because they want to write more papers just because of that? Because you need to write papers to get jobs.
I think that is a problem. But I think the problem is a little deeper. And maybe it is nothing that people are able to help at this point. Science has gone through so many steps that now you need to learn a lot to understand really what is going on. So if you really want to work with black holes and the information paradox, wouldn't you think that people should at least know Hawking's original calculation, either from his paper or some review article or a textbook, and be able to reproduce the actual quantum fields on curved space calculation that gives you entangled pairs? And then you would expect people, if they are using string theory, to at least know string theory to the point where they can compute, let's say, the tension of D branes and the scattering of strings of each other and of D branes. But most of the young people I meet these days who are actually working with black holes and information, many of them tell me they are not experts in string theory, and nor do they know the original work of Hawking of quantum fields in curved space. They're simply playing with bits and moving them around.
Right.
And what has happened is that people just don't have somehow the time or the ability to learn all the many steps that have happened to understand what is the problem they are solving and what are the tools that they have. So I think really it is something for the community to decide. It's not the fault of those people, obviously. It's the fault of the community to decide, how do we teach people all the essentials? Maybe by having better summer schools, maybe by having better review articles, by more coherent review articles, which put everything together. But also by having conferences where all different kinds of people come and meet in one place. Because what has happened is that people who are working on all these bit models and page curves and so on, they're not talking to the people who work on, let's say, fuzzballs, or people who work in the GR community. All the communities have become isolated and closed on their own. And I think that may also be contributing to the problem. But most of the young people who are writing these papers don't actually know what problem they're really trying to solve, in the sense that they have not worked through Hawking's original calculation.
But do you think that even if there are, so as you mentioned, that we can have more comprehensive review articles, but even if there are review articles like that, do you think that people will actually, younger people will actually take time to read them, because they have this pressure that you have to write papers? So I think that's the main motivation for them, not reading the review articles.
I agree. And it's a problem that the community has to get together to try to solve, to prevent completely meaningless work from coming out. Right. So as I'm saying, there is something to be clarified at this point about this entire story which is going on, because I have been working in this field for about 30 years. I have read all the papers on islands, talked to almost all the people I could talk to, and I still can't put together a coherent story. So I can't say that it is wrong because I don't understand the story. So if after reading this whole thing for 2 years, 3 years, and talking to people and not being able to just write down a calculation from top to bottom saying, this is how the page curve comes down by this argument. If people can't understand what you're saying, who actually work in the field, there is something wrong, either with the work or with the communication. So something clearly has to be fixed, because I have really tried to understand what's going on. As to what the solution is, I'm actually worried that these days people don't find essential to even learn string theory completely. So if you ask somebody, do you know string theory? They say, I'm an expert on ADS CFT, but I don't know string theory. And to me, that statement doesn't make sense, because ADS CFT doesn't exist if you don't have an exact string theory. If you just extract some essential rough ideas of what works at low energy from ADS CFT, and then you try to apply it to a difficult fundamental problem like the information paradox, where you need to understand what the string theoretical structure or the quantum gravity structure of a black hole is, you really don't have the tools to do it. So how are we having people in the situation that we are not having people go through a full string theory course, and yet we are trying to have them work on the black hole information puzzle?
But here's the thing. I mean, you just said that you have seen people who don't know full string theory. What do you exactly mean by that? For example, if there is a person who has read the 2 volumes of Polchinski, would you consider that person to know full string theory?
Absolutely. Absolutely.
Okay.
But I'm talking of people who have not read the volumes of Polchinski. And so people who cannot actually reproduce the scattering of a string of a D brane, for example. And so if you talk to them about, what are the different bound states of a D1 brane, a D5 brane, they say, we are not really understanding what you are saying. That's not okay. But 2 volumes of Polchinski is a lot. You don't even have to know that much. I think Polchinski is a difficult book. I'm sure there are a few simpler books. You need to know a little more than Zweibach's text, because you have to know supersymmetric string theories. But if you know both volumes of Polchinski, that's a lot. That's completely solid string theory. And I would be very happy if everybody working in black holes knew that. Much less effort than that is just to learn enough quantum fields on curved space to understand Hawking's original calculation. And one can just read, for example, the nice 2D article on that by Giddings and Nelson from the mid-90s. There's a 2D calculation of Hawking's entanglement calculation. It's just one paper. If you take like 2 months, you can understand all that. If they understand the full quantum field on curved space as per the Giddings and Nelson paper, they understand the entanglement problem. And then they learn string theory at the level of Polchinski, or, let's say half of that. And then they should know how the Strominger-Waffe entropy is derived, because you have to understand the black hole.
Right.
If you have these 3 things with you, I'm good to go from there. Then you can talk to the person and you can argue, okay, what are you doing with your entangled pairs? What happened to the small corrections here? What are your bits doing? But I can't have these conversations with the younger people, because they say, we don't actually know what's happening on the string side, or we don't really know the Hawking's calculation. And then one cannot proceed. If somebody knows all these tools which I just mentioned, then we should definitely sit down in one room with them and say, okay, what are you saying? Why am I not understanding what you're saying?
Okay.
Why am I finding that what Marov is saying is different from what Pennington is saying, which is different from what other people are saying? Why am I in this confused situation? Please clarify.
I see. And to clarify the Polchinski thing, of course, if somebody has read the 2 volumes of Polchinski, of course you need to read. You need to read more, because Polchinski came out around the time when ADS-CFT was being developed, so it does not talk about ADS-CFT, on a deeper level. So of course you need to learn more if you are looking, trying to work on, for example, compactifications. Compactifications is also something that he just goes through. It does not, explain in great detail. But yeah, of course, if as you said before, that if somebody has gone through the 2 volumes of Polchinski, that's very good string background. But what you were saying before is that people don't even know how to do a scattering calculation between a string and a D brane. I mean, for that you don't even need to go to volume 2. I mean, there are some hints to that in chapter 8 of volume 1, right?
Absolutely.
Right.
That's what I'm saying. 2 volumes of Polchinski are overkill. But the difficulties I've been having are at the following level. I was talking to some people about the final steps in the review article by Malsina and others about the island paradigm. And it says out there that, well, the island somehow the black hole has the inside like Hawking wrote, and the radiation outside is like Hawking wrote, but the island represents the outside. And so we should really think of the entropy of entanglement of the, even though the island is inside, we should really think of it as outside. Okay, the words made no sense, but I think a lot of people have commented that they don't understand the conclusion at the end of that review by 4 authors, which was Malzin and others. I don't remember all the authors. But it
Hartman. And,
okay. I would love to understand that statement. What is being said? And so you talk to people about saying, okay, let's start with the black hole. You have the entangled pairs. They are increasing the entanglement. And now you're saying, no, the inside of the black hole is really not there. It's really outside. Just tell me as a GR person, what are you saying different from what Hawking said? How is the information automatically outside now? You're repeating the same entanglement. You're seeing the page curve go up because you're showing the outside is entangled with the inside. But then you're telling me the bits inside are actually not inside. They're actually outside. I don't see that. And they cannot tell me what they are saying. So I need to understand the physics of what's being done. I need to at least talk about quantum fields in curved space and the bits being entangled at the horizon. At the same time, as I talk to the same person by saying, is the black hole like a solid object, like a fuzzball, or is it like a bunch of branes? In that case, where is the inside? So I need to be able to talk about branes and quantum fields on curved space and entanglement with the same person at the same time to understand what on earth is being said. And nothing makes sense to me. And I can't find a person to clarify this with.
I see. Okay, so I have some questions that I had from the people when I announced this podcast. Some people asked questions to ask you. So the question is that, what is Samir's thinking on Suvrat's holography of information proposal?
So I have tried to read several papers of Suvrat, and as I said, they did not make sense to me because he somehow has not even used the tools of string theory in his later work. He says that all that is not relevant. And he's just saying that gravity, just by the fact that the Wheeler-DeWitt constraint puts a certain constraint on wave functions, tells you that information is always both inside and outside, that you can always read off information from far away if you can, if the information is in the center, it's really not localized. And I don't think that makes any sense because it is always coming down to an issue of measurement. Because if you actually just look at the Hawking puzzle in an operational term, which is how I like to see it, I go to the LHC, I make a black hole by colliding 2 particles, I make a small black hole, it radiates 100 quanta, and it evaporates. Now, it's a very well-defined question to ask if these quanta which I have gotten, are they in a pure state or an entangled state? What experiment will I do? If you gave me a spin, just take one spin, and you ask me, is it pure or is it entangled? And I can do the same experiment many times, so I can get the same spin. But I want to tell you if it is pure or entangled. I do have a way of doing that. If it is a pure state, then if I pass it through a Stern-Gerlach experiment, suppose it's something in this direction of x, a pure state in direction x, it will always pass through a Stern-Gerlach orient in the direction x with 100% probability. So try various different Stern-Gerlach experiments, once in z direction, once in the y direction. After some time, I'll find, oh, this guy is in x. It always goes through x. If the spin was entangled with another spin somewhere else, like in a singlet state, it doesn't matter which Stern-Gerlach I pass my spin through, there'll all be a 50-50% chance of going through plus x or minus x. Mm-hmm. So you can always look at a spin and tell me whether it's entangled or not. So the information paradox is just an operational question. You go to the LHC, you collide 2 particles. Let's assume you make a small black hole, it radiates in 100 quanta, you collect those quanta, and you ask, are they entangled or not entangled? Okay. What is Suvrat Raju saying? He's not actually even trying to answer this question. If you have a smooth horizon, they will be entangled because you get Hawking's pair correction. A small correction theorem tells you can't fix that. Okay. So then you're in the puzzle. You're finished. If you don't create a smooth horizon, you create a fuzzball instead. Then all your difficulties are actually trying to show that how do you get the fuzzball? You need all the string here to do that. Okay, but once you've got the fuzzball, it's like a piece of coal. And there's no question to answer after that. So what is the question that Suvrat is trying to answer? He's somehow trying to answer something which has nothing to do with the information puzzle. He's somehow trying to talk about some notion of information and saying that information available at infinity and inside at the same time. I can measure at infinity something which is inside without having had the time to go in and check there. Firstly, I don't think it's true. I think causality is still respected in full quantum gravity. But I wanted to emphasize that whether you can actually check the state of something and know the state of something, it actually has nothing to do with the information puzzle. Information puzzle really is whether when you collide two particles and create a black hole and collect the radiation, is that in an entangled state or not? It's not a question of saying, do I know its information from here or can I measure the information there or not? If I pass the particles which have come out through a Stern-Gerlach experiment, will they always go through in a particular direction? I can compute with my string theory where they go. If it's a unitary evaporation, I pass through that Stern-Gerlach, it will always go through because it's in that state. If it's an entangled situation, it doesn't have any state. It's psi1 tensor psi1 prime plus psi2 tensor psi2 prime. It's a sum of many things. It can never go into any one projection every time you do the experiment. That's all the information puzzle is telling you. And when people try to ask this question, even Marov sometimes talks about, is the information always at the boundary? Is it inside? These questions they have nothing to do with the information puzzle. It's just a question about entanglement, which is a measurable thing. You repeat the same experiment many times and check whether the output is entangled or pure. It's a measurable thing. And which of these is it? That's what Suvrat is saying. But somehow he's not answering the question at all because he's not, I think, addressing the information puzzle. He's asking about something else. Can we somehow say that information is here rather than say it is here? It might be an empty question in the sense that information is something you want to do something with. Like if something is entangled, you say it's entangled. It means you pass it through a Stern-Gerlach, it will not give you the same answer every time. So that's an operational question. Whenever people try to say information is always at the boundary in some way, I think usually those questions don't make sense.
I see. Okay, so the next question is actually about your work with, I think in the 80s with Sunil Mukhi and Ashok Sen on the classification of rational CFTs. So the question is that what led to that paper? I mean, what were you thinking? What you three were thinking before writing that paper? The specific question is that was classifying RCFTs the only goal, or were you trying to do something else too, but you just ended up doing this one thing?
Okay, so that was a very interesting time in the field of string theory because string theory was just developing. And we were all just trying to learn it. And it was all very confusing. And I was just learning a lot with the help of Sunil Mukhi, who was a more senior person there. And he knew a little bit of string theory. And we were all trying to sit down together and just learn what's going on. And then Sunil gave me this problem of trying to find the correlation functions of various things, like currents and so on. Mm-hmm. And then Sunil always has a good knack of finding out what's the next thing you can do. And so a lot of people had found correlation functions on the sphere, but not many people had found correlation functions on the torus. So then I and Sunil got together and we found correlation functions of things on the torus. And then when Ashok Sen came, then we all got together to finding even more complicated correlation functions on the torus. And we were just having fun trying to see what things we could compute with other people didn't know how to compute. And in the process of doing that, we realized that to compute correlation functions on the torus, the methods other people were using, mapping them to free fields or using the water entities, they did not work. But what we found was that we could actually write differential equations for these guys and thereby get an equation whose solution would give us the correlation functions. So it was just something we started doing because we were trying to solve the problem of computing correlation functions. And then we found that, we can at least write differential equations for them. And then Ashok suggested the easiest thing is to actually do it for characters. And so instead of looking correlation functions of operators, we just wrote the equations for characters. And then characters have the special property that their coefficients must be integers. So you even get a discrete number of solutions. And so from then on, it turned out, okay, if you can only get a discrete number of solutions, then now we have a complete way of finding all possible allowed characters. We figured out how to write differential equations for them. But we don't want arbitrary equations. We only want those whose solutions come out in terms of positive integers. And when you try that, you find a classification of these theories coming out. So it's not like we started trying to compute the classification of theories. Everybody at that time did want to know what is the classification of theories. Nobody knew how to do that, but that wasn't what we were directly trying to do. I think it always can be useful to just like compute things which can be computed or which are slightly just outside your range and try to compute that. And then in a rich field like conformal field theory, things just keep popping out. And that's why this thing sort of just popped out at the end of that. But in recent times, Sunil Mukhi has taken this much further, and I think they have very many new interesting results in the last 2 or 3 years in those directions again.
I see. Okay, so the next question that people asked was that, do you know if there is a new non-perturbative prediction from the fuzzball paradigm that we have not observed?
Okay, so certainly that's interesting to me because I've been trying to apply the fuzzball theory to learn something about cosmology.
Mhm.
And what fuzzballs are telling us is that something new happens at the scale of the horizon. Right? So at the horizon is the place where the light cones turn inward. So you get what's called a closed trap surface, and everything has to then keep going inside. But if you look at the cosmological horizon, it's actually the same scale and the same problem. It's just turned inside out. Outside the cosmological horizon, everything is forced to keep expanding. It can't even sit in one place. It has to keep going outwards. But otherwise, the cosmological horizon is just like the black hole horizon. It's an anti-trapped surface instead of being a trapped surface. So then you might think that fuzzball should tell you something about the cosmological horizon and give you novel effect of the cosmological horizon in case they have to give you novel effects at the black hole horizon. So in terms of this thing I had mentioned before, the Vector hypothesis about which were helping us with black hole to see what can go wrong at the black hole horizon.
Yeah.
When we apply that to cosmology, we get interesting effects. We could account for things like the cosmological constant. But something which comes up even before the cosmological constant is that you get an extra energy which is induced when you change from the matter radiation dominated phase to the matter dominated phase. And that is sort of automatically came out of the computation. And that's very interesting because these days people are having a little mismatch of the Hubble constant. It's called the Hubble tension problem. The little mismatch of the Hubble constant between early and late times. And people have found that they can resolve that tension if they assume there was an extra source of energy injected into the universe, but lasting only a short time, just around the time of the radiation to dust transition.
Mm-hmm.
Interestingly, the effects we found from fuzzball theory in cosmology were just short-lived bursts of energy that come when you go from an expansion at the rate of t to the half to a rate of t to the 2/3. So I think it's just very interesting to me that you can qualitatively get effects of the same scale at the same time that you need to resolve some puzzle which people are seeing in the sky. Of course, data in cosmology is very difficult to come by. So it may be that the Hubble tension goes away for other reasons. But while it is there, it's very exciting. And for the same reason, we may also get something like the cosmological constant effects, except we couldn't find any reason, as we talked about at the start of this discussion, why the constant should be exactly constant. It sort of keeps trying to go down.
Yeah.
But the recent results from DESI, even though they are very tentative, also suggested that it's not exactly constant, it slightly wants to go down. So certainly it makes it very interesting for me.
I see. So the next question is that, do you think that the fuzzball paradigm says anything about white holes?
So I don't have a good answer for that, except to say that cosmology in some sense is like a white hole. Right? When we think of cosmology, the Big Bang, it's like a white hole in the sense that everything comes out of it. And you have an anti-trapped surface at the cosmological horizon, which a white hole also has, just the light cones are all reversed. So to the extent that we are talking about the Big Bang, we are talking about a white hole. And so that's exactly what I was just saying about applying it to cosmology. If you want to make a white hole, like in the lab, the way you can make a black hole in the lab, like you can collide things and make a black hole. But I don't know that you can make a white hole the same way in classical dynamics because it starts with a singular initial condition. Now, of course, if the fuzzball theory is true, then you have neither black holes nor white holes. They're all just like pieces of coal. You can make a piece of coal by taking a lot of coal dust and compacting it, but you can also reverse the process. It's just like ordinary physics. Light cones don't go in and they don't go out. They're just like ordinary pieces of coal. So what we need to understand is what happens at the horizon and removes the horizon for the black hole, and what happens at the horizon for cosmology and shows us new effects which maybe explain things like the cosmological constant and so on. So those are all absolutely interesting questions, and I do want to think about them.
I see. So we do know that how hard it is to quantize D branes. So do you think that we will ever be able to quantize D branes, or do you think that that's impossible?
So let me see if I understand what you're asking. D branes are themselves already quantum objects in the sense we understand all their excitations in terms of open strings attached to D branes. So we have quantized them in the sense that when we got D Branes in the first place through the work of Dai, Lee, and Polchinski, they came to us as objects whose quantum dynamics we understood. So we do understand how to do scattering of strings at one loop of D Branes, for example. But the strings are at one loop, not the D Branes. If you want D Branes themselves to run in loops, if that's what you're asking, I can imagine that's more complicated. But a lot of things have been done with D Branes. For example, the very non-perturbative quantum dynamics of D Branes involved in brane-antibrane annihilation. That was the work done by Ashok Sen and others, which is called tachyon condensation. So you have a brane, antibrane sitting on top of each other, and then by using open string field theory through a cubic interaction, you can explain the annihilation of a brane antibrane. And that's a very quantum process. It actually uses cubic string field theory. The string field theory is used at a classical level, but that's because you have a condensate of strings. But brane antibrane annihilation is a very quantum process.
I see. Actually, you mentioned string field theory. That brings another question to my mind. I have seen that a lot of string theorists are, or let me rephrase. A lot of string theorists I've seen that have this fear of learning string field theory because they say that it's a very difficult subject to learn. Do you agree with this, fear, or do you think that these are more like overhyped fears?
Yeah, so I think it's not so much a fear. There is a bit of learning curve because you have to learn something which people like Ashok Sen and Barton Zweibach set up for us many years ago in the early 90s. You have to understand the gauge structure to understand what are the physical states in string field theory. So that takes a bit of learning. Okay, but they have written nice papers, and I'm sure these days there may be a review which you could learn everything from. I think the reason people haven't learned string field theory more is that there is no obvious problem to which you can apply it to get an answer that you don't already get from perturbative string theory. So the one place where string field theory was really useful was the thing I just mentioned, the brane-antibrane annihilation, where open string field theory was very directly used. But there's no similar application that I know for closed string field theory. And closed string field theory also has this problem that it has an infinite number of vertices. You can write open string field theory in terms of only a cubic vertex, but the work of Zweibach showed that to write closed string field theory in terms of vertices needs polynomial interactions of all orders. So somehow it's also not a clean theory. And you really have to have a question you want to solve using that. So for example, if you knew that you could solve the dynamics of black hole formation through closed string field theory, I think people would jump in and learn it immediately. Okay, but the place where it was left at the end of the work that Zweibach did was he set up perturbative string theory in a language where you could see it as closed string field theory, but there wasn't anything you could do with it which you weren't doing anyway with perturbative string theory.
I see. I mean, people have proved a background independence using string field theory, but probably that's not that lucrative of a problem.
So you can do that. It's a perturbative thing. From any background, you can move perturbative to the next background. And that's a good thing to know. But it's something people believed in anyway. You can expand around any background and you should do perturbative string theory. So it's the difference between, what string field theory is doing for you at these levels is that you're computing a Feynman diagram. You can do it by using string field theory by, A and A Dagger operators. Or you can just use it by doing world lines of some particle. Just do world line particle theory, but allow many particles to join and break. So just if you do world line particle theory, that's like doing string worldsheet perturbation theory, which we all know. Or you can write the same thing in terms of A hat and A hat dagger from some field. But in the end, the Feynman diagram calculation is about equally difficult both ways. So the only time the field theory actually becomes useful is that you have so many particles that form a condensate. Then you really want to use the string field theory. And that happened in this cubic string field theory for brane-antibrane annihilation. But we don't have any other case I know where you actually want to use a condensate of strings for something.
Okay, but do you think that you can use string field theory for the fuzzball paradigm, or probably that's too complicated?
So I don't have any immediate direct way of using it. But what I'm saying is if there was a way that it would tell me something about fuzzballs, I would definitely go and learn it. I mean, it's a very nice thing to learn. And I think the papers are good and they are clean. They do take a bit of learning, but I think it's the application that one needs. For example, when brane-antibrane annihilation came up, people learned the required string field theory quickly and they did use it a lot.
Okay, so the last question that I have from the people is that what do you look for when you accept new PhD students?
Yeah, so I think these days what has happened is that we are more and more looking for students who come with a large amount of background,
Mhm.
because people have to finish their PhD in 4 years so they can apply at the end of 4 years to graduate in 5 years. But if somebody comes to do a PhD, but for example, doesn't know general relativity, quantum fields and curved space, quantum field theory, and string theory, then they will take at least 2 years to learn all this, or maybe 3 years. But then they only have 1 or 2 years to write some papers and apply. It doesn't even make sense. So clearly, somebody who hasn't done a master's before coming is already essentially ruled out. Like if you have the knowledge of just the basic undergraduate curriculum from a usual 4 year college in the US, you typically haven't done quantum field theory or string theory. And
Mhm.
even though you can, in principle, learn those in grad school, these days there just isn't enough time because there's so much to learn. So typically, I'm only looking among those people who have taken all these courses and done some projects where they have learned, done something with string theory as part of their 5 year master's program in, somewhere. And then in that process, so when they come here and I say, okay, here is a black hole, and can you just compute the geodesics around it for me and see if a quantum field will fall in or not? They can just go ahead and do that off the bat the day they come here. And if they have to learn GR from scratch after coming here to be able to do that, even though they are capable enough to doing it in due time, we don't have the funding to support them for that time because they have to apply at the end of 4 years.
Well, but people become adjuncts after 4 years, so probably they can survive 1 or 2 year.
Yeah, there are always ways out. So this is not a hard and fast rule,
Mhm.
but it just makes it that much more difficult because if you're not writing papers right from the first or second year that you come, uh, then you may not have enough at the end of 4 years
Mhm. True.
to be able to. If you have, let's say, 5 papers at the end of 4 years, you will probably definitely get a postdoc, or at
Mhm.
least you're likely to get a postdoc. If 4 years have passed and you've written one paper, then unless the paper is something very fantastic, you may have difficulty getting a postdoc.
Mhm.
Uh, think maybe easier in India, for example, where it can take more time to do a PhD because funding is not so tight. There are many students per university, but given that
Mhm.
fundings are very tight in the US, you don't really want a student to take 7 years to do a PhD. So even though
Yeah,
the
for
people who
7
come
is
with
too much.
yeah, even though people may come with less knowledge and they are completely capable of learning it, if they are given an extra 2 years, it's just more difficult to get that kind of support.
In this regard, do you think that there is a big difference between US and Europe?
I do think so. People coming from Europe, they sometimes the academic rigor there is much higher, especially for
Mhm.
people coming from France, Germany.
Yeah.
They have a very strong training in both math and physics, and they are coming with very strong backgrounds. I think the graduation time is much shorter in the UK. Uh,
Mhm.
so I think the UK people suffer a little bit in consequence of that. They have a 3 year undergraduate, and a PhD is also like 3 years,
Yeah.
and you can at most push it one more year. But in Europe, they have a bachelor's, the analog of a master's, then a PhD could also be take a solid 5 years, and so people just pick up so much more because ultimately people are smart everywhere, but you do need the time to become mature. Otherwise, you get rushed through the system. If you get rushed through the system, even the years you spend, you're always on a little bit of shaky ground. So you never become very solid, and you can't really pick up things in the way that I would like people to pick up things. You need to have confidence.
Right.
For confidence, you need to have clarity. But for that, you can't be rushed through things.
So, would you recommend anyone who is applying for a theoretical physics PhD in the US to have at least one master's before applying?
So I wouldn't say about all of theoretical physics. I would certainly say for string theory, because
Mhm.
somehow string theory piles a little bit extra over and above everything because you need to know general relativity and quantum field theory and string theory. And
Yeah.
then if you want to work in black holes and all the work which has been done in string theory up to and including black holes. And that's just too much. So with a bachelor's degree, it's almost impossible to start off directly.
Mm-hmm.
So hopefully, if
And
your master's is focused towards that, it's much better.
I mean, and when you say learn string theory, I mean that also requires background in CFTs and supersymmetry. That's also something that's
Absolutely. All those are
that
big issues because just the way the field has piled up, it's certainly no fault of the students or their advisors or the funding agencies. It's just that the learning amount that you need is so large. It's virtually impossible to know enough to be able to do anything. If you need 10 years to learn, who is going to give you support for 10 years by the time you learn everything? So
10
people
is not
just get
much.
caught in picking up things that the advisor tells them, and you try to grab bits and pieces and move along. It can work or it may not work. It just depends on how well you work with the bits and pieces and how many bits and pieces you actually come across where you're working. But I think it's a very difficult situation. It was much easier the time I was doing string theory because string theory was just starting. So there wasn't all that much to learn. You learned the conformal wheel theory of the Bilavin-Polico Samrachika paper. You learned some, quantizations of the worldsheet theory and so on, the no-ghost theorems and so on. And you can start calculating like anybody else. But now it's become so hard for people.
Right. So I think I said that this was the last question, but there is one last question that I want to ask. So when you're doing your PhD or, as a general, when you are a researcher, there are a lot of times when you are in a state of confusion and you don't know what the result will look like, or probably you don't even know if you can do this calculation or not, something like that. So has there been a time in your long career where you were in this kind of state that you didn't know where this particular research project is going?
Well, almost all the time, because that's what I like to take as research projects. So, for example, when I was doing my PhD, I just came across a problem. I was actually working in astrophysics at that time. And I came across a problem that if you have an elliptical galaxy, it has some kind of a distribution of stars. Nobody knew whether it actually supports small oscillations. Will everything damp out or will it continue oscillating periodically? And I kept working on it for 1 year, 2 years, and nothing would happen. I just couldn't figure it out. And at the end of it, I found lots of techniques in function analysis and measure theory and so on, which had been developed for quantum scattering theory by the particle physicists and also many mathematicians. And applying them, I could get a solution to the puzzle. But there were no tools available. It wasn't even clear the puzzle could be solved. And so most of the time, you're just lost and confused. But I think that's a good state to be in because if you're always working on things which you just do and the answer comes out, you do more and the next step comes out, I think you'll never actually hit you cross a new threshold. And after when I started working at MIT as a junior faculty, I wanted to solve the black hole puzzle because I've been thinking about it even in my PhD days. I said, now I have some years, I just think about it. I didn't write any papers. I just sat and thought about it for 5 years. And it was just a mess. Every time I thought I got something, it would just slip out again. Because I would keep trying something. I thought it works. Sometimes it works for 1 day, sometimes for a month, sometimes for 6 months. And then you yourself find the mistake. This is not working. And at the end of about 6 years, when we start playing with things which were coming up in string theory, suddenly in 97, we got this idea, all the string sets are expanding. They're actually like fuzzballs. And that's the answer. But if you've been sitting on something for 6 years with no progress, you understand the problem so thoroughly that the moment there's a small glimmer of light somewhere, you know this is it. But I sat for 6 years on this without basically writing anything. And it is extremely stressful, of course, because people think you should write papers. But I think if you keep writing papers and keep doing things which can be done, that also eats up all your time. You could keep writing papers on, supersymmetric things and BRST and this. A lot of things were going on at that time. You can keep writing those, but not actually tackling the really big problem. But if you think, first you should choose a physics problem and say, I want to solve this problem. Then give it whatever it needs. But if you just say, let me see what I can do with what's available, then I think you just end up doing small things here and there, which may just meander around. But the chance you'll actually solve something might not be that high.
But as you were, mentioning that state of confusion that you were in for a long time, I mean, you can correct me if I'm wrong, but I think this is right that you can afford to do that if you have a permanent position. But if you're a PhD student, that's very stressful that you're not doing anything, right? So how to
But I
deal
did
with
both
that?
the times when I couldn't afford to it. As a PhD student, I
Okay.
put 4 years into this problem of solving the small oscillations. These days, people use it. I mean, now it's been checked numerically soon after, and now people are saying they can even observe these in the plane of our galaxy and so on. So it's exciting to me that it's now being used by people in that community. But I just spent 4 years doing this with really almost being able to write nothing at that time either. And so I didn't actually get a good position in astrophysics, but I was learning string theory by then, and I got a postdoc and came to US to Harvard to do a string postdoc.
Mhm.
I just left the field. But then MIT again, I put 6 years into doing this. Even though I got the solution just at the end of that, it was too late to get tenure there. And so I left it again and I came to Ohio State. So I've never actually been able to hold on to a job because this is what I always do. And so the last 5 years again, I've just tried to understand what's going on with cosmology and to solve what I was calling the vector hypothesis. So again, I'm not writing papers in fuzzballs because I can always write more papers with fuzzballs. But I think
Mhm.
there's something really to understand, like what happened in cosmology, and to really see what's the lesson we get for quantum gravity out of all this. And so again, I don't write any papers. But I think that's very important. Even when whether you can, if you always wait till you can afford it, I think even when you can afford it, you may not end up tackling a big problem. So I think one always has to take that risk. But I think
Mhm.
even if you don't take a big risk, I think all I would say is you should always think about a physics problem you want to solve and then go and see what tools you have, rather than saying, I have these tools, so let me see what I can do with them.
Okay. I mean, I also remember this example that, for example, Polchinski didn't write any paper in his PhD. But when I think about these examples, I have to remind myself that these times were late 70s or early 80s. So, but can a PhD student do that today?
No, I think it is much more difficult, and you're absolutely right. It has become basically very hard to do this. And I think this is a problem the community has to solve in a coherent way. We are not putting enough time or energy. In fact, it's going backwards. We are reducing the PhD times. People are not doing masters, they go after the bachelor's for a PhD, then we reduce the PhD time also. And all that at the same time that the amount of things they have to learn are actually growing. So, how is this ever going to work? Somewhere things have to crack. And the way they are cracking is that people don't understand what they are doing. And so sometimes what they're doing might come out to be completely nonsensical, but you can't even help them to understand that what they're doing is nonsensical because they don't have the tools to understand what's the question they're trying to answer. And so things have really gone off the rails, I think. And you're absolutely right. In the early times, it was always possible to survive because there weren't that many people. The field wasn't that hot. There weren't that many papers flying around. There wasn't the archives, which allows you to access papers more quickly. So people could sit down and think about a problem for a long time. But I would still say that physics can really be done if you sit and think about a problem for a long time. And we are not making that possible. I think it is maybe that in places which are not very competitive, for example, still smaller universities in India or somewhere, you could sit down and think for a long time if nobody's bothering you. But
Mhm.
you should first want to do that. I mean, there are many places where you have the opportunity to sit down and think for a long time. But people still enjoy the fact they're writing papers, which gets you invited to conferences, gets you citations, gets you promotions. So people have to realize that that's not necessarily the best way to do physics. It produces a large volume of stuff, but it may not actually be producing new directions or solving
Right.
anything really.
Okay, so I think my questions are over. Thank you so much for your time. It was great to talk to you.
Thank you.
I
This
hope
was very
that
nice.
I will invite you later, probably with some other guests. Let's see about that. I mean, actually, I was thinking of inviting Oleg to this podcast as well, but I don't know if he's free right now. But probably I will invite you with him someday.
Okay.
Okay. Thanks again for your time.
Okay.
Thank you.
Thank you.